Welcome to the next part of the module on Android concurrency frameworks, which completes our coverage of the AsyncTask framework. The previous video discussed how AsyncTask embodies key characteristics of frameworks, such as their support for inversion of control, domain-specific structure and functionality, and semi-complete portions of applications. This part extends this earlier discussion by examining two common types of frameworks, black box and white box, described at this link. It also demonstrates how AsyncTask contains elements of both black box and white box frameworks. The first type of framework is the black box framework, where application developers only need to understand the external interfaces of its classes. Elements in black box frameworks are typically reused by parameterizing or assembling instances of these classes. The second type of framework is the white box framework, where application developers must also understand some parts of the framework implementation. Elements in white box frameworks extend base classes and override their hook methods. Black box and white box frameworks are based on different types of patterns. For example, black box frameworks are often developed using patterns that emphasize extensibility via object composition. Examples of these types of patterns include strategy or decorator, described at these links. Likewise, white box frameworks are often developed using patterns that emphasize extensibility via subclassing and overriding of hook methods. Examples of these types of patterns include template method or state, described at these links. To make the discussion of black box and white box frameworks concrete, we'll show how AsyncTask contains elements of both these types of frameworks, which helps application developers extend and customize its capabilities. We first examine the white box elements of the AsyncTask framework that enable long-duration operations to interact and communicate with the user interface thread. The AsyncTask base class uses the template method pattern to define the program skeleton of an algorithm in its execute method, which defers some steps to subclasses, in accordance with the white box framework design principles, as described at this link. After the execute template method is called, the AsyncTask framework dictates the subsequent flow of control and invokes the onPreExecute hook method to perform the initialization actions in the user interface thread. When this hook method returns, the framework dispatches the doInBackground hook method, which runs in a background thread and can thus block while performing long-duration operations without affecting the user interface thread. When doInBackground finishes, its results are returned via the onPostExecute hook method, which performs operations that must run in the user interface thread, such as displaying an image to the screen. Although the variant of the template method pattern used by the AsyncTask framework follows the canonical structure of the pattern, which involves overriding hook methods, it extends the pattern by allowing hook methods to run in different threads of control. We now examine some black box elements of the AsyncTask framework, which enable application developers to configure the number and behavior of threads that run in the background and perform async tasks concurrently. AsyncTask uses the strategy pattern to select its internal concurrency model at runtime. The default concurrency model used by AsyncTask has changed over time, as described in the discussion on order of execution at this link. In recent releases of Android, the default behavior of AsyncTask is to use a single background thread in each process to run all doInBackground methods of tasks, thereby avoiding common application errors caused by concurrent execution. AsyncTask concurrency model can be configured via several different executor strategies. The default behavior is implemented by a serial executor strategy, which executes tasks one at a time in sequential order within a process. Some applications, however, benefit from the ability to run multiple async tasks within a process in parallel. For example, to take advantage of multi-core chipsets. To support this use case, AsyncTask instances can be configured with a thread pool executor strategy, which executes multiple long-duration tasks in parallel within a process. The AsyncTask framework also supports custom executors, which application developers create by implementing the executor interface to define their own concurrency models. The executor interface defines a strategy that enables runtime configuration of concurrency models that implement executor. These strategies can be passed to an async task via its executeOnExecutor method or by calling its undocumented setDefaultExecutor method. These executor strategies are treated as black box plugins by the AsyncTask framework, so there's no need to subclass AsyncTask to configure different concurrency models. Regardless of which concurrency model is configured, the AsyncTask framework ensures that all hook methods are synchronized in such a way that certain operations are safe without making explicit synchronization calls. In particular, member fields can be set in the constructor or the onPreExecute hook method and safely referred to by the doInBackground hook method. Likewise, member fields set in doInBackground can be safely referred to by the onProgressUpdate and onPostExecute hook methods. In summary, the AsyncTask framework combines black box and white box techniques and patterns, which enables application developers to easily extend and customize its capabilities. In general, white box frameworks are easier to develop because their design needn't anticipate a wide range of use cases, since that's the responsibility of application developers that extend and customize their base classes or interfaces. They're also harder to use, however, because application developers must understand more framework implementation details, such as which hook methods to override. Conversely, black box frameworks are harder to build because their interfaces and control flow must anticipate a wider range of use cases. However, they're easier to configure and use since they're customized via self-contained plugins, which enable dynamic variation of framework behavior without extending or changing framework code, as described at this link. The AsyncTask framework applies several Gang of Four patterns. For example, it applies the template method pattern to implement its white box capabilities, so users must subclass it and then decide which of its onPreExecute, doInBackground, onProgressUpdate, onPostExecute, and onCancel hook methods to override. After an application running in the user interface thread calls an AsyncTask execute template method, the framework invokes these hook methods at different points of time and in different contexts, such as in the user interface thread or one or more background threads. Likewise, AsyncTask applies the strategy pattern to implement its black box capabilities, which enable applications to dynamically configure predefined or custom executors that designate which concurrency model to use when running async tasks within a process. It also applies the post-it2 half-sync, half-async pattern to guide the design of its internal concurrency structure and functionality,